Hey everyone, welcome to Science in Perspective. I'm going to look at three papers in this episode and take a look at something that kind of binds them together, a common theme among those. These papers have nothing to do with each other. They're not about the same topic. They're all obviously in science. But as I like to do, I'm going to find kind of the binding theme between these areas and actually argue in this episode that what binds these together is an approach that I think is good for science in general and good for mathematics, good for using kind of mathematical modeling in a more creative fashion. I'll get into all that. But let's just go ahead and jump into the papers themselves. I'll talk obviously what they are about, and then I'll show how these kind of a core inherent pattern is analogous between them, and kind of there's a connective tissue between these studies that I think is really worth focusing on. So one paper that came out recently is it's titled Quantum Dissipative Continuous Time Crystals. Quantum Dissipative Continuous Time Crystals by Russo and Pohl. That's out of the Institute of Theoretical Physics in Vienna. That came out in September 2025. So what's interesting just about this topic generally is it seems to be a new phase of matter. Now, this is a theoretical paper. It points to things that definitely could be experimentally validated. There are experiments that are related to time crystals, but the continuous time crystal model is a purely theoretical thing, but it's using quantum mechanics as, basically right out of the textbook and then just combining it in a new way. So it's using very established science. It's not crazy theory. And it's showing a really interesting property in the modeled material. Okay, so what is a continuous time crystal? Basically, if you think about what a crystal is, right? It's a periodic array of atoms, right? Although really in 3 dimensions, but you can kind of let's just do it in 2 dimensions for simplification. Think of like a checkerboard or a chessboard, and you put an atom on each one of those squares. And then you have this repeating pattern of atoms, and that's essentially a crystal. I mean, a lot of materials, especially the more ordered ones, are going to have something analogous to that setup. And you've got all kinds of symmetries in there. And what these authors do is they model a system like that. So basically a bunch of atoms, they're arranged in, a repeating pattern. They do 2 dimensions. They can extend it to 3, but they do predominantly 2 dimensions. And they set up the system in such a way that they're capturing, kind of where the atoms are and what their energies are, the kind of laws that govern the dynamics of that system. And they do that in a way that it's invariant. They use a time invariant Hamiltonian to model that system. Okay, and I'll get into what that means in a bit if you don't already know. But just understand that it's time invariant. So meaning, when you model a system like this, you don't expect anything to change in time. You're just kind of defining it, almost in a static fashion. Static is not the best word because you're still capturing the dynamics. Dynamics, things move, but the laws of the Hamiltonian don't change over time. You see this with the use of things like the time-independent Schrödinger equation. Basically the same idea. Hamiltonian would be involved in something like that. It's a time-independent mathematical expression of the particles and the energies and everything that essentially makes up the system. But what they find is that when they start to find solutions to that mathematical expression, those solutions show something new. And the new thing is basically a temporal symmetry breaking. Over time, it shows that the arrangement of some of the energies within that crystal start to break symmetry. So you can kind of think of breaking symmetry. We normally think of that as something happening spatially. So if you go back to that checkerboard, you got all those atoms and they're arranged in a periodic fashion. So kind of like no matter where you look, they kind of repeat the pattern, essentially like tiles on the floor. And then if you were to kind of dislocate those atoms, like maybe you have a shearing force on the material and it shifts atoms against each other, that would be like a breaking of the symmetry, right? They no longer look the same everywhere. Well, you can do that in time. You can see that maybe spatially nothing is changing, but certain energy levels, kind of quantum observables, as you might say, end up reorienting themselves so that there's a new configuration of matter, but that only happens over time. And it's kind of a surprising result because, you're looking at something which spatially just stays the same as a crystal, and there's nothing in the mathematical description that says it's supposed to change over time. But then if you solve for solutions of that mathematical equation, such as you start to look at what happens over time, it looks like something changes. It's kind of a way to say it at a super high level. So that's interesting. So interesting that they actually think of this as a new form of matter. Again, theoretical, but the prediction of a new form of matter. When you think of a form or a phase of matter, this is like solid, liquid, gas, obviously, but you also have things like superconducting materials, plasmas, things like that, right? Basically, Bose-Einstein condensates, which we've talked about before. Matter that is a completely different configuration than anything that can be explained with the already existing phases would be considered a new phase of matter. And that's what they think this continuous time crystals are. Okay, so that's kind of interesting, and you can go check out that paper, Quantum Dissipative Continuous Time Crystals. Quantum, because they're setting this up quantum mechanically. They're using a Hamiltonian, they're using what is effectively, a Schrodinger equation to model the system. Dissipative, because the way that they set up the system, not only are they saying where are the atoms and basically modeling the crystal with a Schrodinger equation, which again, if you don't know, is basically just in quantum mechanics, you think of things as waves, and the wave equation was done by Schrodinger. So the Schrodinger equation is basically allowing you to calculate the wave function. The wave function kind of captures everything you know about the system, or everything that you could describe the system as is supposed to be contained within what we call a wave function. Colloquially, we just think that matter seems to move like waves, right? Particles and waves, but there's a wave aspect to them. So that's where the Schrodinger equation comes in. The dissipative part is because beyond just modeling the crystal, they have basically a laser coming in, what you would think of. It's a driven system, so you can think of that as a laser if you were to do this experimentally. It's pumping energy into the system, and it's also dissipating energy as that's happening, which kind of sets up its own steady state. So it's like the energy's coming in, but the energy's also going out. So it's not really a dynamic system in that sense. That's just kind of, it's basically pushing something out of equilibrium and then keeping it there, right? Equilibrium would be like you're not pumping energy into the system. You just let the system thermalize and everything kind of goes into its own uniformity, right? I mean, literally like a gas in a box. If you just put the gas in there and maybe it's originally hot, but then it kind of cools down and gets to its baseline temperature and everything evens out and everything's kind of the same. This one, you keep pumping energy, let's say, into the box, but the box is also dissipating that energy and getting rid of some of it, and those kind of balance each other out. So it's still kind of a type of equilibrium, but we would think of it as non-equilibrium because it's been shifted by the energy, but now it's just staying in that new configuration, okay? So it's you almost think of it like laminar flow maybe in water. Like if you looked at water coming out of a hose and it's so smooth that it looks like it doesn't move, right? It's its own type of static configuration, but it's a static that's arrived at, a static configuration that's arrived at through dynamics, right? Anyways, so you can kind of think of it like that. Okay, so it's got energy coming in and energy going out, and it's out of equilibrium, but it's still staying still. There's nothing, now that you've got that set up mathematically as a model, there's nothing else changing, right? But over time, it does change. And you can kind of think of a really loose analogy is maybe like a hard drive, right? If you think about a magnetic hard drive, you've got all these, you can call them, I guess, bits, right? Little magnets. Let's just call them little magnets in there that are arranged in a certain configuration. And that arrangement corresponds to, let's say, the photograph that you were saving on your computer, right? It's a dog. And then if I change that to a cat, then the configuration where those magnets are pointing is going to be different. Every unique kind of magnetic orientation or configuration corresponds to a different piece of data, right? That's essentially super high level description of how something like a magnetic hard drive would store information. But the total, let's say the total magnetic energy in this example, I'm not saying this is like real hard drives anymore, but let's say the total magnetic energy always stays the same and the only thing changing is the orientation. It's kind of like what's happening to these continuous time crystals. You have energy coming in, it's dissipating out, it's off equilibrium, but it's all just kind of staying there. But over time, something in the energy configurations are changing. It might be like energy levels, maybe it's like spins of the electrons in the atoms, it doesn't really matter. but some type of quantum observable changes over time and it breaks its own symmetry. Um, so again, I think what's surprising here is you model a system using standard quantum mechanics. You set up the dynamics with that Hamiltonian, which is just a mathematical expression that kind of captures the energies, and it just captures the setup of the system, right? Here are the energies, here's the atoms, here's the electrons, here's what they do. And then you kind of freeze it. It's time independent. Nothing is supposed to change anymore. It's kind of like a static definition of something. And then yet you still see something almost popping out of existence, which is this new symmetry breaking that happens over time. And it's kind of like, where does that come from? So this is an example that I think is, I say popping out of existence, which would probably make a lot of scientists uncomfortable, or anybody interested in science, because, well, what does that mean? It sounds kind of hand-wavy, sounds like you're almost appealing to magic or something. But when you talk about emergence, which is you think about patterns arriving in a system in a way that cannot be deterministically traced back to its constituent pieces, right? Starling murmurations, the wetness of water, whatever example you want to use. The overwhelming amount of nature actually is emergent. I mean, you can't even get past hydrogen on the periodic table without having correlations within the electrons that produce properties that cannot be directly traced back in an analytical fashion to just the individual electrons and the nucleus of the atom. You don't get exact solutions. And that's just helium, right? That's just one electron more than hydrogen, let alone the periodic table, let alone atoms combining to molecules, let alone molecules combining to. And so the overwhelming amount of nature, basically all of it, is actually emergent. They have these kind of behaviors that seem to pop into existence. Pop into because, again, it cannot be explained in the reductionist fashion where you just kind of say, well, here are the pieces and here's how they come together. And that's the causal story of how what we're looking at came to be. You can't do that with emergence, which might surprise a lot of people because isn't that what you do in science? Like you find out the causes of things, and it's kind of beyond the scope of this episode, but yeah, that's it's very naive and reductionist, and increasingly becoming a backwards way to think about science in that very deterministic causal way. So things do seem to kind of you can still characterize them. You can use math to characterize the emergent patterns. You can understand its properties. You can make comparisons of scientifically to those properties in other areas. Still very scientific, but that kind of here's the cause and here's where it came from is just extremely naive, really always has been. But as we start to realize how complex nature is, that becomes much more apparent. So where was I going with this? So we've got this you're characterizing a system with mathematics, and then you find that the solutions, let's say to the Hamiltonian or the Schrodinger equation, show you a new pattern that was never baked into the mathematics itself. So it is kind of like what we think of as emergence, right? Which is what this seems to be in these quantum dissipative continuous time crystals, is the emergence of a new order, emergence of an oscillatory pattern, what you might call limit cycles even, right? We don't need to get into all the jargon, but basically just new patterns that emerge. They weren't put into the mathematics itself, and yet the mathematics had a way of still arriving at the answer. And if you look at the mathematics and the way that the math is able to do this, is because they tend to have interaction terms in there. So, for example, super naive, basic way to do something would be like, here's all my atoms in my crystal, and I'm going to treat all those atoms or the electrons within those atoms as independent, and I'm just going to kind of add everything together. And actually, you still see a lot of that in science, right? Actually, the overwhelming majority, arguably, of science is done in that fashion, I would say, unfortunately. Things are very naively treated as independent, and you pretend like they don't interact with each other. And if you do that, it's a very safe and convenient way. The math tends to work out a lot more effectively, although by effectively, I just really mean conveniently. Like you can get your answers more easily, and you can kind of paint a more causal picture with it, right? This is why you see a lot of people, scientists using Gaussian distributions, which I would argue is extremely unrealistic. In fact, I don't think nature has Gaussian distributions, but let's not get into that now. You can only form those nice bell curves because you assume things don't interact with each other, and then they add together, and then they produce those types of statistics. Even in a lot of science, if you say, well, you might say, well, of course it's in nature because you can go measure things and you see Gaussian distributions. Well, you're measuring things in a very gamified fashion. You're putting a grid on top of nature and then you're counting the grid as though everything's independent, and then you get those statistics. That's not the same as saying the Gaussian distribution is actually the way nature works. Nature, by and far, operates by interaction. Of course, those electrons are talking to each other within the atom, between the atoms, writ large, right? All the way up, whatever high scale you want to go to, up and down. So that independent way of looking at things is not great. But now we're talking about math that at least admits the interaction. And in a Schrodinger equation, you might call this something like interaction terms. You see this in condensed matter physics a lot, because condensed matter, you have to take into account the interaction between the pieces, right? Quantum chemistry, same thing. You're going to model your atoms and molecules. You could do it without the interaction terms. You could use like really baseline kind of Hartree-Fock methods and stuff like that. But by far, a more realistic approach, and obviously a more computationally demanding approach, is to put the interaction terms into there. Get things to talk to each other. If you put things that talk to each other into your mathematics, you're going to get results that definitely align to nature much more effectively. And so that's what this math is doing, right? And I think it's a nice way to add a bit of rigor to the topic of emergence, which unfortunately, but understandably, tends to get kind of tossed to the side as though it's like a niche topic of complexity science, which is not true, because again, as I'm arguing, and as I've been arguing for years, emergence is not a niche side product. It's not an edge case. It's everything, right? It's nature. It's just not convenient to do it in the traditional mathematical sense. So that's what stood out in this paper. Quantum dissipative continuous time crystals, maybe it's like a new form of matter. Yeah, okay, maybe. Like I'm not disagreeing with that, but I'm not sure I find that super interesting, but it's kind of neat. And maybe they'll have interesting uses for, I don't know, could be for data storage. It could be for quantum mechanical simulations, could overlap with quantum computers, right? Because it's a quantum dissipative system. That's cool. But what stuck out, right, is that, they take quantum mechanics, well-established mathematics, they put interaction terms in there, and out of that come solutions that have patterns that were never baked into the mathematics from the beginning. I love that. It's a way to bring math away from kind of reductionism and determinism and kind of overly causal ways of explaining things, and just kind of letting math go, do its own thing, right, and come up with solutions that look like nature. That's more in line with how nature actually works, popping into existence type patterns, right? If you wanted to go mathematically model something like the murmurations in a flock of starlings, people have tried. Well, here's the local interaction rules, and they try to trace the local interaction all the way to the broad correlations that you see in the patterns, and it never really works, right? Because that's not what emergence is. It's not a causal story. It's not billiard balls bumping into each other to produce the final result. It's a thing that pops into existence at its own level. It's not, as they say, right, complexity is not more, it's different. It's not just more of the same thing that you saw at the small scale. So this is a way of getting math to kind of do that, right, which I think is really important. And I think not that this hasn't been done. I mean, interaction terms have been used in mathematics for decades, but this is the type of direction. And more to the point, I think it's good to think of this as letting math go and do its own things in ways that you don't understand. Okay? I think a good analogy to this, more than an analogy really, is what you see with deep learning systems. Okay, deep learning systems, you set up I've talked about this before, I talk about this a lot, but you set up artificial intelligence systems with mathematics, right? You might be using like mutual information within the objective function. You've got calculus there as part of backpropagation. Everything's, it's got the mathematics, a lot of linear algebra in there to get the matrices to come together. But that's not how AI works. That's just the setup. You have to, if you want artificial intelligence to do anything worthwhile, to solve, categorically hard problems, you have to let the math go and do its own thing. So in AI, this would literally be putting the math into the computer and then letting, let's say, matrix multiplication happen billions of times, billions of iterations, until solutions emerge out of that give you things that are surprising, like natural language, like images that have never been created before, songs that have never been created. Genuine creativity, right? Movies now we're seeing. Go take a look at, Grok video, and it's able to create these ultra realistic videos. You can barely tell the difference between that and something that was taken with a camera, with a real individual. And it's creating things that have never existed before. It's mixing and matching things at a scale that is well beyond anything you could do if you actually, tallied up all the pieces yourself, right? Using mathematics. So math is not, things are not being calculated the way people think things get calculated normally in AI. No engineer or scientist alive understands how AI produces its result if you define understand in that causal deterministic sense, because that's just not what it is. You have to let it go. So on a smaller scale, I find this is kind of what's happening with this continuous time crystals. You use math, you allow the interaction to happen, and then and they will use like computing simulation too to derive some of these solutions, because they're complex and you can't do it analytically, right? So you do it numerically, or you do it through simulation, or sometimes you'll even use AI, and it allows the interaction within the mathematics to produce things that weren't baked in explicitly to the mathematics itself. So it's a walking away. It's a letting the math produce its own creative emergent patterns, and then realizing those patterns look a lot like what's in nature. It's a different paradigm of science. It's a different paradigm of using mathematics, and I think that's what's important. Now, it reminds me of some other studies that have gone on. There's another one, completely different area, called Vortices and Rotating Solitons in Ultra-Light Dark Matter by Brax and Villegas. And that's out of France, right? The Université Paris-Saclay, pardon the pronunciation. But this is in May of 2025. So now we're talking about cosmology, right? We're talking about dark matter. We're talking about topological and geometric structures that, exist and presumably emerge within, the fabric of space-time, right? We're talking about space, right? And we're talking about galaxies and how galaxies form and why they're there. And if we take a look at the standard dark matter kind of theories that have been around for a few decades, it's kind of normal matter, dark matter. So it's not normal matter, but it's kind of modeled as like heavy particles that kind of interact and do things in a classical fashion. And presumably that provides some of the gravitational landscape that is supposed to exist to make galaxies spin the way they do, for example, right? So if you take a look at galaxies and you notice the rotation, let's say speed, you'll say, okay, well, the gravity from the sun, the stars and whatever's supposed to be in the center, whether that's a black hole or just a dense cluster of stars, that doesn't seem to explain the rotational velocity or maybe the angular momentum that's there. There must be something else. And so these dark matter theories have kind of emerged as something that might help explain, where does the extra gravity come from to make galaxies spin and do what they do, essentially. But the kind of classical dark matter, which you might call even heavy dark matter or cold dark matter, it doesn't seem to be explaining the observations that you get when you take a look at the cosmology, when you take a look at how things like galaxies form and behave. So there's another type of dark matter that's been proposed, which is ultralight dark matter. And ultralight dark matter is not the heavy, usual kind of cold dark matter that behaves classically. They think that or in a quantum mechanical fashion. And what's interesting about that is, the holy grail of theoretical physics is really to try to bring quantum mechanics and relativity together, right? The math doesn't work together. So you're always, a lot of theorists are trying to come up with kind of quantum descriptions of gravity, or at least quantum descriptions of what we see in space, right? Like the cosmological structures and the filaments and the things that are going on in the universe, galaxies and rotations and all this. Is there a quantum mechanical description that we can have of that? So in this paper, what they do is they take a look at the dynamics of this ultralight dark matter, and they find that when they set it up mathematically, they start to get solutions. So we're kind of seeing the parallel to the other paper I just talked to, right? They'll set up something, it's a similar idea, really, Hamiltonian. You're doing quantum mechanics math, and so you're going to have a Schrodinger equation in there, and you're going to try to find solutions to that Schrodinger equation and see what it gives you, right? Now, this setup is quite a bit different than the continuous time crystals, but in spirit, it's kind of the same idea. Here, they're going to basically establish, well, really what they're doing, actually, and I think this is super cool, is they're taking the mathematics from condensed matter physics or quantum chemistry, and they're basically trying to explain space with it. is a high-level way to think about it. Because if you look at things like the mathematics that have been kind of traditionally applied to Bose-Einstein condensates, they'll use that type of mathematics to say, hey, maybe that's what's going on in space. Maybe that could actually help explain galaxies, which is really odd at first blush, because the mathematics of things like atoms and molecules and Bose-Einstein condensates is all about the small, right? Quantum's always about the small. Now you're using it to explain the large, which has always been the realm of general relativity, which is kind of one of the reasons why, again, the math for the small doesn't seem to work for the math for the large, right? But now they're saying, maybe it's almost like, there's a massive wave function that exists in a quantum sense that helps explain what we see in galaxies, right? It sounds kind of crazy, but it starts to produce results that seem to match up with what we see cosmologically, right? So they will establish things like scalar fields, and this is kind of standard quantum mechanics, right? Think of a field as essentially an array of numbers, super high, complex numbers, right? It's got imaginary parts in it, but really just like an array of numbers. And you say, okay, well now if you, let's say, operate on that kind of like a matrix, right? That array of numbers, what happens to it? And what happens to it is you start to get patterns emerging within the mathematics itself that were not baked in there from the beginning. So the math they typically use for this one is it's kind of like a nonlinear Schrodinger equation, right? Because they start to put interaction terms. There's self-interaction in there, and that self-interaction comes by way of it's kind of like what you would normally do is take the interaction terms from electrons, and now you're kind of making the interaction terms part of gravity. It's like you're putting gravitational terms within the nonlinear Schrodinger equation, which is fine. Because, who's to say what the forces of electrons are? What are they actually? And this is just another force. It's gravity. So why not just plop it into the equation and see what happens, right? And you get this kind of version of a Schrodinger equation that is nonlinear, that has the interaction terms, kind of similar at a super high level to what we were seeing with the continuous light crystal. And then you start to solve it and you get solutions out of it. And what happens is you start to see the emergence of patterns like vortices and solitons, okay? And we don't need to worry about exactly what those are, but just think of it as you're using these kind of fields, like arrays of numbers, and you act on them and you try to find solutions with them. And what ends up happening is, let's say, the phase within that field starts to kind of quote unquote twist in a certain way. And it starts to look like what we think of as more classically vortices, right? So, if you take like your canoe paddle and you put it into the lake and you see a vortex, a little eddy form, right? And you were to describe that classically with mathematics, well, the math kind of looks like what's happening inside these scalar fields of the mathematics that are used in the nonlinear Schrodinger equations to describe ultralight dark matter. Okay, I hope that's not too jargony. Don't worry about all the little pieces. It's just, again, they're using the math from atoms and molecules and condensed matter, and specifically things that seem to take on a single wave function, like Bose-Einstein condensates, when all, let's say, the electrons are kind of acting in the same way and they become coherent. The mathematics that explains that type of coherence might be what is happening cosmologically. And so they model it like that, and they find that when you solve the solutions to those equations, you get things like vortices and you get things like solitons. The soliton would kind of be like an ultra, maybe dense behavior towards the center of the galaxy. Okay, so it'd be the solutions would have aspects of the wave function that you're solving for that would show a lot of density towards the center. And, maybe that's related to the black hole if it's at the center of the galaxy, or maybe it's a precursor to the black hole. I don't think they really know, but it's that kind of idea. And then these vortices are a distinct emergent pattern that comes out of the solutions. And what role they play, it's hard to say. It might be somehow indirectly related to maybe some of the bending of space-time that you get from relativity, but this is kind of a non-relativistic look at things, so it would be very indirect if that were the case, assuming relativity is involved, which is probably a safe assumption. But anyways, I'm not trying to say there's a connection there. It's just, maybe there's an indirect influence of the vortices within the solutions that affect space-time in a certain way. But basically what it's doing is it's not a description of gravity itself as much as an explanation for maybe how the gravitational setup is what it is when we look at things like galaxies. Again, you're trying to explain things like the rotation speed, right? So high level is like, yeah, take the stuff that we do in like quantum chemistry and condensed matter physics and then apply that to basically a wave function description of cosmology to show what galaxies are doing. But again, you're getting these patterns coming out of the math. You can look at the interaction terms. Think of the fields as being, again, like a big array of numbers, and another big array of numbers. You square the term in the equation. So those are getting mashed together. They're self-referencing. It feeds back in on itself. And when you get those feedback loops, this is true of all complex systems, and again, really all of nature, it's the self-referencing, it's the feedback looping that starts to allow patterns to emerge. In this case, it's vortices and solitons. In the continuous time crystal paper, it was translation symmetry, a reconfiguration, let's just say, of quantum observables within the crystal. It doesn't really matter what it is. It's just the emergence of well, it might matter to you depending on what you're interested in. But I'm just saying, for the sake of this argument, right, that self-referencing is where you're getting the emergence of patterns. You're getting solutions in the mathematics that weren't baked into the mathematics originally. So that binds those papers together quite closely, I would say, because they're both quantum systems in this case. And they're, in both cases, you set up the model and you're using out-of-the-box quantum mechanics, like well-established stuff. And obviously your setup is a little bit different because there's something novel here happening from a theoretical standpoint, but still, it's not like crazy math. But you're adding interaction terms, whether that is electronically or gravitationally. You get feedback loops from that, and out of that pops, just from the mathematics, solutions that contain patterns that were never there to begin with. And you might say, well, maybe that's kind of like standard in science and mathematics. Well, not really, actually. A lot of times, the patterns that you end up getting were still kind of there to begin with. Obviously, you didn't know what they were, but the model more deterministically predicts what you were going to get. You see this with a lot with differential equations. You see this a lot. There's a certain circularity there, right? It doesn't mean the pattern you looked at wasn't surprising, but it was already kind of part of the dynamics of the way you set up the system. That's not what we're talking about here. Here, it wasn't even in the dynamics of the system at all. It's just the only thing that was there in the setup was the feedback looping, right? Kind of like in AI, you will set it up, and then you set it up in such a way that it can keep feeding back in on itself and self-referencing itself, and out of that comes the emergent pattern. I want to call one more paper into account here. So we got time crystals, and then we got, this ultralight dark matter. There's another paper actually back in 2017 called Period Doubling Cascades of Limit Cycles in Cardiac Action Potential Models as Precursors to Chaotic Early After Depolarizations. So a bit of a mouthful. Basically, take-home message here is it's a paper about trying to model the rhythms in a heart, right? Heart rhythms. What are they? Where do they come from? We know why they exist. You got to pump blood throughout the body, but why does it look the way it does, right? Why does it have, where does it emerge from, right? How does it establish a self-sustaining rhythm? And why is it not always maybe the exact same rhythm? There's differences in the rhythm, right? They used to think that those differences were a problem with the heart. Now it seems like the heart is supposed to have not the same exact rate all the time, and that's actually an adaptive feature. So that there's a whole area of research around, heart rhythms, right? And in this one, again, I'm not going to go into all the details, but what they're doing in this study is they take mathematics, this time ordinary differential equations, right, coming right out of calculus, standard stuff, and they use those ordinary differential equations to model things like ion channels and, calcium ion flows and voltages, and basically the, membranes and all this kind of stuff, like the potential between membranes and all this kind of stuff. the way that the heart is set up and where that energy comes from to drive the actual beating and produce the actual rhythm, they model that. You can use that with ordinary differential equations, which in some sense is pretty standard. But you've got more than one dependent variable that's in there. You have one independent, let's say with time, with an ordinary differential equation, but you add these other terms that are, again, kind of self-referencing. You start to add squared terms or cube terms. Right out of that paper, there's like a cube term. So you model it, and then you find solutions to differential equations, which is standard, but the solutions don't automatically, they're not like a deterministic prediction the way you often use calculus. They are solutions that look very different than anything that was baked into the mathematics from the onset. And as it turns out, those solutions are what they call these limit cycles, which is, again, a kind of periodicity that just appears, right? It comes out. And if you look at that periodicity, there's nothing in the original equations that had it. It wasn't like you were even trying to set up a periodic system, right? In the way that this is periodic, which is the same as the other ones, right? You might be modeling the spatial arrangement of atoms in a time crystal, which is periodic, but the laser that's driving, if it's a laser, whatever the energy is that's driving the system had no periodicity in it. And the periodicity that emerged in the time crystals was a temporal periodicity. It wasn't something that was done spatially. So anyways, if that's too much jargon, just understand that it wasn't there in the mathematics to begin with. That's not how it was set up, and yet it still emerged. Same with the gravitational stuff, right? It's not like vortices and solitons, right? These densities of things that emerge, not like those are put into the mathematics. That's not in the Schrodinger equation, and yet when you start to solve the solutions with that setup, you get them. In this case, you're getting these rhythms, these periodicities. Limit cycles is kind of another way of thinking of an oscillation, basically. All limit cycles are oscillations. Not all oscillations are limit cycles, but it's a type of oscillation. And you're seeing that emerge, and the one that it's not a random thing. And when you look at it, it's a self-sustaining emergent pattern that happens to match up quite closely with the rhythm of the heart, right? So scientifically, it's a nice pairing between what you do mathematics. But again, it's not like you're defining the system with the math and then getting this kind of natural evolution that leads to a solution in any deterministic causal sense. It's not a causal thing at all. You can't know where those patterns came out of the mathematics. They just did. And that is the essence of nature. That is how we should be modeling things. Okay? So those are 3 studies that I wanted to point out that in the way that I'm arguing in this episode are doing the same thing, right? Quantum dissipative continuous time crystals see the emergence of a periodicity over time. Vortices and rotating solitons in ultralight dark matter are seeing the emergence of the vortices and the solitons through this nonlinear version of a Schrodinger equation that they find solutions for. And these limit cycles in cardiac action potential models through those ordinary differential equations that they find solutions for have a type of periodicity as well. So I think that's beautiful. Totally different areas, right? Crystals, galaxies, and heartbeats, right? I don't think any of these researchers know each other. I don't think. They're working on completely different things. But there is a beautiful binding synthesis between them that I think says something important for science writ large. Okay? That's really all I wanted to do in this episode. And I think I'll be doing that a lot going forward, is I want to show how different studies at some interesting abstract level are actually doing the same type of thing, and how that meta-level analysis says something really important for science going forward. I think that's a strong addition to science in general. I think it's important to think like that. And understanding those patterns will help you understand science a lot better, because you can't research all the different papers yourself. But if you understand what binds a lot of them, right, it raises the level of your understanding to the level of synthesis and allows you to understand a lot without having to know specifically all the details. Anyway, so that is it for this episode. Thanks everyone for listening. And for those of you who are watching, just really quickly, if you want to become a member of Science in Perspective, go ahead and check out science-in-perspective.com and become a member today. Premium members get access to techniques and mindset videos. These patterns that I talk about are not just relegated to science. They can help you make decisions in life. It's a more analytical, rational, logical way to think about things. You can take on some of the attitudes of the way scientists tend to view the world, and you can involve those in your own life that tend to be really, really effective at you making decisions. Could be in finances, could be in relationships, could be in, negotiations, or it could just be the way that you're thinking about health. Whatever it is can make a big impact. So techniques and mindset videos help with that. Becoming a premium member also gets you access to visual concepts summaries, so you can actually poke around and see the concepts and how they relate to each other for every episode that I do. There's a forum on there for chatting. That's where the community lives. There's high-level 5-point summaries that you get. There's the transcripts that read more like an article, and if you enjoy the reading, and a few other things on there as well. And you can you can come back where you left off on the videos and all that good stuff. So go ahead and check out scienceinperspective.com. Links are in the description. There's also a Patreon link in there if you'd rather go that route and become potentially a premium member today. Okay, thanks everyone for listening. And again, for those of you who are watching, until next time.